Friends, a number of disciplines are involved over a long period to develop P&IDs that are good for construction. Fresh engineers who can demonstrate P&ID skills will not only excel in interviews but also in their technical roles in the EPC companies. In this video, we will go through how to read a P&ID and also we will go through the underlying principles that go into the development of P&ID. As we go through this P&ID, some of the questions that may come up to the young engineers are: why are two pressure relief valves located on the column top, whereas a single relief valve on the steam condensate part? Why is one relief valve having a bypass around it? What is the significance of LO and LC marking on some of the relief valves? Why notes like no pocket, free draining appear on the P&IDs? Why are two pumps shown at the stripper bottoms? What is the purpose of the bottoms pump recycle? Why are no isolation valves shown on the reboiler inlet and the outlet going back into the stripper? The path to answer these questions lie in understanding the principles behind the P&ID development. Once you know these principles, you can confidently interpret, answer, and develop P&IDs, and you will be capable of providing justification to the P&IDs that you develop. Using the SOR water system P&ID, this video will take you through those very principles that form the backbone of every P&ID. Let's first start with the PFD of the SOR water stripper. This stripper operates at 0.5 bar gauge. The heated SOR water enters the tray at around middle of the column of the SOR water stripper at about 80 degrees Celsius. A reflux stream at 90 degrees is drawn out at one tray above the feed tray. The reflux is pumped through a cooler and fed to the top of the stripper at 60 degrees Celsius. An intermittent stream of oil can be removed whenever there is a buildup of oil in the internal reflux stream. The stripped gas leaves through the top outlet of the stripper at 90 degrees Celsius. The column bottom at 120 degrees Celsius is pumped away after exchanging heat with the feed stream. A reboiler is provided at the base of the column to generate vapor that will enable the stripping action. Steam is the heating medium that is supplied to the reboiler tubes, and after exchanging heat with the stripper bottom's water, the steam condensate is taken away from the reboiler tube. Ensuring safety is the first principle that is utilized in the P&ID development. Why? Because most of the chemical plants that handle hazardous fluid at high temperature and pressure. The key requirement of any hazardous chemical facility is that it should be safe to operate and should not cause any harm to the people, environment, or to the facility itself by way of a fire, explosion, or release of toxic chemicals. Of course, incorporating safety features is ensured throughout the design process. The P&ID presents the opportunity to coordinate and ensure uniform safety requirements across various documents developed by different departments during the engineering. It conveys the key safety requirements to all the users. Now, let us quickly go through the SOR water stripper P&ID to glance at the safety features that are incorporated. Pressure relief valve. At the top of the column, we see that there is safety valve that is set at 3.5 bar gauge. It means that the safety valve will pop up at 3.5 bar gauge and ensure that the column never exceeds 3.5 bar gauge. It means that the column is designed for a design pressure of 3.5 bar. Another pressure relief valve. This pressure relief valve is located on the condensate part and this is set at 7 bar gauge. It ensures that condensate part never exceeds the design pressure of 7 bar. It also means that the LP steam design pressure is 7 bar. The third safety feature on the P&ID is the line designation details. Sample line designation is 20-inch P107A1A-H. 107 is the line number. P indicates the service of the process. 20-inch is the size of the line. Now let's look at what is A1A. A1A is the pipe specification. Basically, it conveys the rating of the pipe or the thickness of the pipe and the metallurgy of the pipe. Next is the indication H, which indicates the insulation requirements on the pipeline. Next is the alarms and the notes. You find that there are alarms on the temperature indication on top of the column, high, high and low, low. Now the low, low temperature is there in order to ensure that the operator can take action if the temperature goes below a certain level. At a certain temperature, the condensate condenses on top of the column and can cause corrosion on the line. That's why you see that the top of the line is steam traced. You see notes like free draining and no pockets on the pipeline. It conveys to the piping engineer that this line has to be free draining into the destination and there should be no pockets on the column overhead line itself, so that no condensate is collected on the line and which may become corrosive in nature. Moving on. Here is the sour water P&ID, and circled are the locations where safety features are incorporated on the P&ID. Another feature is the airfail conditions of the control valves, which enables the control valves to go to fail-safe position on instrument air failure. Next, let's look at the layers of safety. Safety in an operating plant can be expressed in layers of safety. The layers are shown in the picture here. These layers are indicated in the P&ID. Each higher layer can be activated if the lower level layer fails. This creates a system with subsequent levels of safety to help prevent catastrophe from occurring. The goal of safety is not to reach the top of the triangle, but to stay as close to the bottom as possible. This shows the importance of inherently safe design process. Regulations provide a baseline for engineers to operate when designing a chemical plant. They have brought safety to the forefront of design. Although you can never eliminate these upper layers of process safety, but by designing a process robustly, major process safety incidents can be avoided. The second feature that is very critical to the development of P&ID is the operability. Operability is the ability to keep a piece of equipment or a system in a safe and reliable functioning condition according to predefined operational requirements. It can be broken down to flexibility, accessibility, ability to monitor and control, and ensure efficient operations. It is also important to develop safe operating limits for various equipment or the envelope in which it will operate safely and reliably. Operational flexibility can be related to startup, shutdown, and other plant bypass and recirculation features that are provided to enable operators to continue operations in a safe and reliable manner. This aspect will be separately presented to you. Now let's look at the flexibility features shown on the sour water stripper P&ID. You see that the control valves are given block valves at both sides of the control valve, and a bypass is provided around the control valve. This is a flexibility for the plant to remain operating even when there is a problem with the control valve. When a control valve gets into a problem, the operator can go and open up the bypass and ensure the flow keeps going on, and they can shut down the control valve by closing the inlet and the outlet valves and take it for maintenance. Another flexibility feature that we saw was the spare safety valve. So there is a LO and LC marking on these valves. The LO is a lock open valve. So the valve that is locked open, the safety valve is online, and the valve that is LC marked or lock closed valves, it shows that that's a spare safety valve present online. So the operator can change over quickly while the plant remains running. So summarizing, this is the sour water P&ID, and highlighted here are all those sparing and flexibility requirements that we discussed just now. Let's now look at the accessibility features. Accessibility features are better shown on piping layouts, but in P&ID there are some process critical requirements are shown. Like for instance, on the sour water P&ID, a note is shown on the side stream takeoff valve, and it is written that the level gauge should be seeable from this operable valve, so that the operator can watch the level gauge and manually open the valve to drain off the oil and close it whenever the level goes down. So these kind of features which are critical to process are noted on the P&ID, whereas there are many more accessibility features for maintenance and operations that are not really written down on the P&ID. Further, let us look at the monitoring and control aspects. Here on this Sorwater P&ID, we have several control schemes like feed flow control, top pressure control, the reflux control, the top overhead temperature control, which controls the temperature of the reflux stream coming into the Sorwater, and also the steam flow and the bottom condensate level control are existing to enable safe operation of the column. Now let's go into the reliability features that are available on this P&ID. We have the pump minimum flow concept shown on the P&ID. The pump casing vents, and the pump also has a low level alarm on the column bottom, which enables the pump to remain operating and never starve for water. And the corrosion probe that we discussed previously is a reliability feature on top of the column line to prevent or to identify corrosion issues early and take action. There are other examples such as filters and strainers are provided on streams which have solids particle that can cause problem downstream. Exchanger back flushing schemes are shown on P&ID, which enable online flushing to remove particles that pick up on the tube side of the exchangers. So this is the Sorwater P&ID, and shown here are all the reliability features that are discussed right now. So it gives an overview of various facets that are shown on the P&ID that enable reliability. For instance, we didn't discuss this point. On the reboiler inlet and the outlet, we have temperature measurements in the DCS to ensure that the temperature never increases too much, which can cause fouling in the reboiler. Now let's look at the another feature or principle that is very critical for the P&ID development, that is maintainability. Maintainability is the ability to isolate, flush, and purge the equipment before it can be given to maintenance, and to remove the hazardous and the flammable materials from the system. Vendor manuals generally provide information for the requirements of the maintainability to be provided, or companies have some kind of a standardized approach which are already given on standards, and the engineers can utilize them to show the minimum maintenance requirement. Further, reviews such as design review and hazard reviews are good opportunities for the operations and other safety people to review these requirements. Here is the P&ID, Sorwater P&ID, summarizing all the maintainability requirements on this system. You have valves on the column, around the column, to enable the column to be shut down. Now let's have a look at the stakeholders for the P&ID. There are 4 key players who have a stake in the P&ID development, and in fact in the whole process plant design, construction, and operation. They are the regulators, owners, operator, and the designers. The severity of process safety incidents can be very high. You might have heard or read about the Bhopal incident in the 1980s. The regulators or the government has come up with regulations based on internationally accepted rules to make the owners comply with the EHS or Environment, Health and Safety rules and ensure safety of people, environment and the facility. All have to comply with the law of the land. Now let's look at each of these stakeholders. What are their pulls and pushes? The owner is mainly concerned about cost, payback. He doesn't want any gold plating of the plant. The owner sets the priorities for safety, cost, and the schedule. Some projects are schedule driven, and some are safety driven, and some are more focused on cost. The operator, on the other hand, is more focused on the flexibilities required to start up, shut down, operate, maintain the plant. The operator requires reliable, flexible, and a safe operation. Simplicity of operation, trainability to methods may also be a concern for the operator. Now, the designer. The designer needs clarity, consensus, and agreement on the engineering options in order to deliver a safe plant on time and on budget. Changes to decision can have a severe impact on the budget and schedule. And of course, we have the banks, financiers, maintenance contractors, customers who have a stake in the safe and operable plant, but their influence on the P&ID development may be minimum or nothing. But they will have an impact directly or indirectly if the P&IDs are not accurately reflecting the equipment details. Further, let's have a look at the hierarchy of rules that are used for the development of the P&ID and other engineering documents, because there are a number of rules that play out, such as local regulatory codes, owner company guidelines, design company guidelines, and industry practices and codes such as API and ASME. The designer has these rules to comply with. Clarity is often provided in the project guidelines. When the requirements of these codes and standards contradict each other, the hierarchy of rules require that the engineer has to comply first with the local regulations, next with the company standards, thirdly the contractor standards, and finally the industry standards will be applied. There are 5 parameters that are used in the plant operation monitoring. They are level, pressure, temperature, flow, and composition. One of the most important guidance for the plant monitoring is the development of the Safe Operating Limits document. This document is developed by the design team and reviewed with the operations. The operating limit for each parameter is identified that will be safe, taking into account the process safety, environment impact, reliability, and other reasons to ensure effective and efficient operations. Normally, certain clients require the P&IDs to show the operating range of some of the parameters. Operations would have a tendency for having maximum flexibility when deciding the operating range of a parameter. See how. Now, if the operating temperature of a particular equipment is 120 degrees Celsius, say, and the design temperature is 200 degrees Celsius, and that design temperature is normally same as the MAW or the maximum allowable working pressure. Normally, the left-hand side bar is preferred by the operation, where the green is the operating range and the yellow highlighted range is the safe design range. So the operations have the maximum flexibility to operate as close to possible near the design temperature itself. However, the right hand side is the one that is recommended with a red zone implemented, which is a buffer zone. So at the transition between the yellow zone and the red zone, temperature alarm is provided, and at the end of the buffer zone, if required, a safety interlock function can be provided to shut down the unit before the temperature hits the 200 degrees Celsius, which is the design temperature. So a methodology for safe operating limit may be looked at here. The idea for the team is to obtain the historically acceptable operating envelope, taking into account all the modes of operation such as startup, normal operation, and shutdown itself, or any other mode of operation. Then the key limit values of the process parameter are identified based on design limits, mechanical integrity limit, and sometimes there could be some limitations of the instrument that are located on this equipment. We need to identify the equipment and the instrument dependencies, and then based on that the limit values are identified. Having identified the limit values, depending upon the system complexity and risk involved, the limit values for the particular parameter itself is decided based on process subsets and high integrity protection systems that are. The main aim of this exercise is to drive the safe operating limits as close to the operating envelope as reasonably practical. Once this is done, the team evaluates the consequences of deviations from the operating range. So let's take this tank, which is containing a flammable fluid. It pumps out whenever it is required. So in this case, we can see that the green is the operating range of the level, the tank. After that, we have a yellow highlighted range, which is where the operator can do troubleshooting if the level reaches in that zone, and the operator has sufficient time before he can bring the process into control within the operating range. If the operator is unable to bring it into control, then an alarm sounds. It enters the red range, wherein once it hits particular level, then a higher level alarm will sound and it may trip out the put into the tank or outgo from the tank depending upon where the level is. So the tank neither overflows or it empties out fully. So what is done is a sufficient time is provided between the operating range to the high level alarm and to the between the high level and the high level alarm for the operator to be able to take action.